Thanks for joining me. Today we're going to continue our discussion of Lewis structures and how they relate to molecular shapes. Now, the theory behind this is called VSEPR. That's an acronym that stands for Valence Shell Electron Pair Repulsion Theory. And in simplest terms, it says that the shape of a molecule will be formed where you get the least amount of repulsion between atoms or electrons. Another way to say this is that the shape of a molecule's shape right up here, let's get this to go to pen maybe. The shape helps it relate to its properties. So look, if you're a freshman in high school and you're 6'7" and 185 pounds or 205 pounds, you're probably going to get college scouts looking at you for basketball unless you're incredibly clumsy, because your shape tends to make you a good basketball player. Okay. Now for us, a little bit different here. Whoops, that's not what I meant to do. Start one more time. This shape I can represent by these balloons here. So I'm going to label these things maybe 1, 2, 3, 4, and 5. So in the first box, I see two balloons tied together. Now, if you were to try to push those balloons together and let go, they will go back to the shape you're seeing. And it looks something like this, where you have a central atom, I'm going to call it A, with two things attached, B and B. And I call this an AB2 molecule. Every time you see an AB2 molecule, it will be linear. Now, those things, those B's, could be another atom, but at this point, I'm simply just referring to an electron domain. Any region in space that contains electrons, either with something bonded or not bonding, is still considered a domain. So that would have linear geometry or linear electron domain geometry. Now, in this second one, if I would look at it kind of from above, I would see a central atom and then 3 electron domains around it. And those could have something bonded to it, in which case this would be an AB3 molecule. And an AB3 electron domain geometry, the B's get as far away from each other as they can. I could try to squeeze the balloons close together, but as soon as I let go, they'll go back to that same angle. And that angle we see here is 120 degrees between each of those. On the first one, I didn't mention it, but that bond angle is 180 degrees for a linear molecule. On the third one, maybe the diagram doesn't look great. Those balloons should probably be on the bottom, not looking like the ones in 2. They should be pushed down a little more. And it should look something like this, where the two straight lines represent the same plane as the circle. The wedge means one of those balloons is coming out at you, and the dashed line means it's going behind your computer screen. So that if you have an AB4, a central atom with 4 bonding regions or electron domains around it, will have a bond angle of 109.5 degrees. We call this one tetrahedral. I didn't mention on the second one, we would call this one trigonal planar. So these 3 atoms form a triangle in a flat plane. And the first one, I've used the term, but I'll go ahead and write it. You can't really see that. I'll write it up here. Linear. Now, number 4 and 5, I'm not going to ask you to know from my class. I'm going to just briefly talk about those. So for number 3, the fourth one here, it has 5 different domains. So we can see that. Now, 3 of the domains, these 3 that I'm drawing green right now, which are represented by the red balloons, are what we call the equatorial electron domain regions. And they are 120 degrees apart from one another, as you might expect. Then, and I'll use a different pen color, I'll use red, There's one that goes up and then one that goes through that going down. Those are the green balloons. And of course, those are 90 degrees from the plane. Now, if you were to connect these points here, 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 and then connect the triangle, you get a pyramid on the top. And then, of course, if you did that on the bottom, you would get another pyramid. So we get two pyramids. So we call this thing, it has a funny name here, right? Trigonal pyramidal. So it looks like a triangle that forms a pyramid on the top and a pyramid on the bottom. Okay, that's how it gets the name trigonal pyramidal. The last one, if we look very carefully, it has 6 things attached, 6 electron domains. So when you have 6 domains, you have 4 that form kind of a box in the center, and those are all, as you might expect, 90 degrees apart from each other. Then you have some that go up the top and down the bottom, and those are 90 degrees from that plane. Now, if you were to connect the box and then connect all of the corners, you would get right there a 4-sided figure. And if you do the same on the bottom, you will get another 4-sided figure. An 8-sided figure we call an octahedron. So this is octahedral geometry, electron domain geometry. Okay. Now, for my students in first year, I do not need you to know trigonal, pyramidal, or octahedral. All right, we're going to keep moving here. I'm going to try to keep the video under 30 minutes for you. That first one, if you see an AB2, is linear electron domain geometry. If you have 3 domain geometries, that one is always going to be called trigonal planar. 4 electron domain geometries, tetrahedral. 5, if you're being asked, is trigonal bipyramidal in terms of its electron domain geometry. And if you have 6 domains, octahedral. All right, I think you understand the bond angle, the angle forms that is formed when these atoms are connected, right? So I've got 3 examples here. I've got carbon dioxide, I've got methane, and I've got formaldehyde over here. Now, we've drawn these out before. If you draw out carbon dioxide, it's going to be a C, double bonded oxygen with lone pair electrons on the outside. Now, when we look at the shape of this thing and we talk about it, this is linear, right? This is an AB2 in terms of electron domain geometry. Next to the carbon, there's 1 domain, 2 domains. I know a double bond is 4 electrons, and 2 electrons could make up a domain. But a single bond, a double bond, a triple bond, it's still just 1 domain. So that one there is going to be linear geometry, and the bond angle is going to be 180 degrees. That's what it's always going to be when you have a linear geometry. The methane, of course, we've drawn that one out enough times. You recognize that's going to be the AB4 with no lone pairs, and that's going to be tetrahedral in terms of electron domain geometry. And because all 4 of the domains are bonding, it will also be tetrahedral molecular shape. And that will have a bond angle of 109.5. The last one here is formaldehyde. And formaldehyde is the byproduct of, if you were to drink methanol, that's grain alcohol, but it's not grain alcohol, it's wood alcohol. Grain alcohol is ethanol. Methanol, if you drink it, can dissolve your optic nerve, you can go blind, and your body then metabolizes it and turns it into formaldehyde and embalms you. Now the structure of this, if we were to draw it out, is a single bond hydrogen, a single bond hydrogen, a double bond oxygen with lone pairs. Now, the way you want to look at that thing is overall, the carbon, we're only talking about the carbon right now, has 3 domains around it, a hydrogen, and the double bond oxygen. That makes it trigonal planar with a 120 degree bond angle. Now, if we actually took out a protractor and measured it, we would know that the lone pair here and lone pair here cause quite a bit of repulsion and repel each other, and they'd actually force the hydrogens a little closer together. So instead of being 120, 120, 120, well, this one might be, 121 degrees, 121 degrees, and 118 degrees. But for my class, I could care less about that. If you can see that and recognize 120 degrees, trigonal planar, I'm great with that. All right, so let's look at these in a little bit more detail, talk about them again. Here is the Lewis structure of carbon dioxide. It has two electron domains surrounding the carbon. Anytime you have two things, like balloons, whatever, bonds or lone pairs, it's always going to have the same electron domain geometry. When I use the term geometry here, I'm referring to its electron domain geometry. That is different than its molecular shape, or what many authors will call its molecular geometry. Molecular geometry, and I hate that word because you got electron domain geometry, molecular geometry. My students get confused by that. So instead of calling it molecular geometry, I prefer to call it molecular shape. Okay? The shape is what it actually looks like. The domain geometry is just how many things are attached. Because we have two things attached, it is linear. Because there are no lone pairs on our central atom, it is also linear molecular shape because it has no lone pairs. And that's what it's going to look like. Okay, kind of an AB2 generically, thinking about that. And of course, we can see that bond angle there, 180 degrees as you go across and around. All right, next, sulfur dioxide. Now you're looking and you're thinking, wow, I think you messed up because that looks like maybe sulfur trioxide. Well, let's see if I messed up. The Lewis structure of SO2 looks like this. Now, we discussed resonance in an earlier discussion where we said you could actually draw, excuse me, two molecules of SO2 and they would look different, wouldn't they? Where on one side you have a double bond and one side you have a single bond. Both of these exist. Or we could just draw it this way, draw the dashed line representing the resonance structure of sulfur dioxide. Either way is okay. That's not the point for this particular slide that I want to go through. What we want to talk about is the sulfur, that central atom. How many electron domains does it feel? Well, the answer is 3. It feels 1 is a lone pair, 1 is a single bond, and 1 is a double bond. So it has 3 different regions around it, electron domains. That's what I'm showing with my diagram. The B here represents the sulfur, and then the 3 A's are the 3 domains. So if you have 3 domains around something, that's going to be trigonal planar. So 3 things gives it an electron domain geometry of trigonal planar. Now, that is not the shape of this. In this molecule, if you've listened in my class, we would call this an AB2E, where there's a central atom, 2 things bonded, and 1 electron pair. So because you have 1 electron pair, it's going to bend the oxygens a little bit closer together than what you might expect. And so we call this a bent shape or V-shaped molecule. And so this is really our SO2, what it's going to look like in terms of molecular shape. So the shape has to do with how many bonding and non-bonding domains you have. The electron domain geometry, the only thing you need to know is how many domains are present. And the bond angle here, approximately 120, because that lone pair would be on the top, pushing those guys down, okay? It is definitely not going to look linear with 180 degrees like this, that somebody might say, right? As we compare that to carbon dioxide, the previous example, which was linear. All right, let's do methane. If I draw out the Lewis structure, it looks like this. Now, understand it's not a 2-dimensional drawing. We have to be 3-dimensional. So this is an AB4. There's a central atom with 4 domains around it. all four happen to be bonding. Now, anytime you have four things around there, it's going to have a tetrahedral electron domain geometry. And what I said is, if all of those domains are bonding, then the molecular shape is the same as the electron domain geometry. So in this case, they're all bonding. It's also going to be a tetrahedral molecular shape. And if you remember, the bond angle on those are always going to be 109.5 degree bond angle. Doesn't matter where you look. These are 109.5. These here are 109.5 all the way around. That's what it's going to be. And of course, why is it called a tetrahedron? Well, you can see the four faces. You've got the front face here is one face. Then you got this face over here is two faces. Then you got this third face on the bottom, and I didn't show yet, but the back is the fourth face. So a four-sided figure, a tetrahedron. Ammonia, here's its Lewis structure. It has four domains, 1 non-bonding and 3 bonding. So four things attached, or four regions, four things, is always tetrahedral electron domain geometry. But because one of those is a lone pair, this is not an AB4. What we're looking at is an AB3E. One atom in the center, three things bonded, and one electron pair. Anytime you have an AB3E, the molecular shape is going to be trigonal pyramidal. So it might start looking like tetrahedral in terms of geometry, but because one of those is a lone pair, it compresses those hydrogens a little closer together. So it's not 109.5. With a trigonal pyramidal shape, it's going to be about 107 as the bond angle there. All right, water, Lewis structure looks like this. Again, I think you're starting to see the pattern here. It does indeed have four things attached, two lone pairs and two bonds. So we would call this an AB2E2, a central atom, two things bonded, two electron pairs. That is going to have, because it has four things attached, still a tetrahedral electron domain geometry. But because two of them are lone pairs, it's going to end up causing the molecule to become bent. And those hydrogens are going to be compressed quite a bit toward each other. They're not 109.5. That would be with no lone pairs. It's not 107. That'd be one lone pair. With two lone pairs, it gets compressed down to about 104.5. And we call that molecule bent. Some authors call it V-shaped or bent. And again, that bond angle is about 104.5. All right, let's look at hydrogen chloride next. For HCl, here's the Lewis structure. I'm talking about at this point chlorine, not hydrogen. Chlorine has four domains surrounding it, three lone pairs and one non-bonding. So hydrogen chloride has tetrahedral electron domain geometry. But because only one of the four are bonding, we say it is linear. And with three lone pairs and one bonding, you always form a line, linear shape. If you want, we could argue and say, well, there's really no bond angle there because it's just two things and you need a third line to make an angle. That's fine. That's fine. I won't ask you that. Some kids will keep telling me it's 180 degrees and I don't really care as long as they draw it correctly. A little note here to think about. If you have just two atoms, nitrogen, carbon monoxide, oxygen, chlorine, hydrogen, bromide, you could draw them out. Here's nitrogen, oxygen, chlorine, and HBr. In each case, the electron domain geometry is going to be linear. Well, the shape is going to be linear, isn't it? Right? And so is the geometry there. That's just the nature of the way they are. Bond angles, well, with two, they don't make an angle. And the bottom line here is, maybe you know, if you have 2 points and you connect them, you make a line. You always do. That's why they're linear. All right, 20 minutes into this, so I want to try to finish in the next 9 minutes if I can. This is a nice chart. If we were in regular class, I'd have you memorize it, but because you're virtual, you can use it as a reference. It summarizes the things here. This column represent right here the number of electron domains that you have. Then the bonds, if you have two things attached, it's going to be linear. If you have, and that's going to be both its domain as well as molecular structure, the shape. So electron pair arrangement is really what we would call over here the geometry. This is geometry here, electron domain geometry. Molecular structure is what we call the shape that you're going to get. Notice that when the number of things and the number of bonds are the same, you get the same answer. But when the number of things and the number of bonds are not the same, we get different answers, okay? So it's a good summary sheet. Now, for whatever reason, the author of this switched everything around. See, I would have written this A, B, B, and they wrote it A, B, A. And they did that in all of them differently than I did. So I hope that doesn't confuse you. I'm just pointing that out as you think about that. All right, we'll say it another way. If you have two electron domains, right, then the geometry of that electron domain geometry is linear. If you have, and it looks kind of like this, doesn't it? There's an AB2. If you have three, it's going to be trigonal planar, and it kind of looks a little bit like a Mercedes symbol, I suppose. If you have four, it's going to be tetrahedral. And if you have five, again, I didn't ask you to know five for my class, it's trigonal bipyramidal. And if you have six, it's going to be octahedral. Now, the possible molecular geometries, what I've been referring to as shape, is a little bit different. With two, the only thing you're going to get is linear. With three, though, you could get trigonal planar, or you could get bent. The trigonal planar would be an AB3. The bent would be an AB2E. I'm not going to draw out additional examples. You can try to draw those out and see that. Tetrahedral could be any of these. If it's tetrahedral, if it's an AB4. If, though, you have an AB3E, it will be trigonal pyramidal. And if you have an AB2E2, it's going to be bent. So it starts to get more complicated. When we get to trigonal bipyramidal, then we have to start worrying about the axial atoms versus the equatorial atoms and so on. And we end up getting trigonal bipyramidal and linear and seesaw and T-shaped and octahedral. Boy, it gets even more complicated. We get all of these different shapes, okay? Now, I'm not going to ask you about all of these shapes down here for my first year class, okay? AP, we worry about that, but not here. In terms of, let's kind of just take it back and make sure we understand. Electron domain is any region in space where electrons are found. Now, we know electrons repel each other because they have a negative charge. Now, they could be, if they're in the electron domain, they could be bonding electrons, and that could be a single bond containing 2 electrons, a double bond containing 4 electrons, or a triple bond containing 6. And these would all be covalent bonds. That's one type of electron domain. The other type of electron domain would be what we call non-bonding domain. 2 electrons on a single atom. We call that a lone pair. So electron domain is either bonding or non-bonding. Those are the two things they could be. Now, for ammonia, NH3, there are 3 bonding domains and 1 non-bonding domain. The lone pair is the non-bonding domain. Now, it contains 4 total domains, so its electron domain geometry is going to be tetrahedral because it has 4 regions around it. But its molecular shape is not tetrahedral, but trigonal pyramidal because that lone pair of electrons pushes these hydrogens down a little bit, okay? So we always want to be aware of the difference of the term electron domain geometry and what many books call molecular geometry, which I like the term shape for better, the molecular shape. What is the shape of the actual molecules, okay? So they both contain 4 domains there. It's just a matter of if they're bonding or non-bonding. And then we know, of course, that the reason it takes the shape it is so that those domains want to get as far away from each other as they can. And those non-bonding lone pair electrons aren't attached to anything, so they can kind of bully the other atoms around there, if we can personify it as such. All right, let's keep moving here. In terms of electron domain geometry, again, there's 5 basic domains or electron domain geometries. And here they are listed: linear, trigonal planar, tetrahedral, trigonal bipyramidal, and octahedral. Those are the geometries. And they depend only on how many domains you have. If you have 1 domain, it doesn't exist here. If you have 2, it's linear, 3, trigonal planar, 4, tetrahedral, 5, trigonal bipyramidal, and 6, octahedral. Okay? The molecular shape is related to how many are bonding and how many are non-bonding, and how they orient themselves in space. That's the shape. And we'll summarize those for you on the next slide, as well as the handouts I give you in class that will have those drawn out for you, okay? So I'm not doing more on that right now, but here I've listed on the left side the different electron domain geometries, what they are. And anytime you have 3 domains, it's going to be trigonal planar, 4 domains, tetrahedral, 5 domains, trigonal bipyramidal, 6 domains, octahedral. Now the shape is on the right. So if you have an AB3, 3 domains, or an AB2E, 3 domains, you either get trigonal planar or bent. For the tetrahedral geometry, you could have tetrahedral if it's an AB4. If you have 4 domains where 3 of them are bonding and 1 is non-bonding, it's trigonal pyramidal. If you have 2 bonding and 2 non-bonding, it is bent. And again, I am not asking any of these shapes in my class down here. We do that in AP Chem, not in our first year class. They're summarized for you here again, if you want to kind of look at that as a reference, okay? Now, there's a summary slide here. I'm not going to read that to you. You can pause the slide at this point if you wish. That is a very quick review of VSEPR, valence shell electron pair repulsion theory, with an explanation. Hopefully you now know the difference between an electron domain, which could be bonding or non-bonding, and a molecular shape, the way it actually looks. Thanks for watching this one all the way to the end. Good luck with your chemistry studies. Take care.